Welcome to today's video. Today we're going to talk about differentiation rules. So far we've talked a lot about differentials, partial derivatives, directional derivatives. We've seen a lot of examples. We've seen how to compute those. What we haven't seen so far is rules for general multivariate differentiation that somehow generalize the rules that we know from one-dimensional differentiation. And of course, most of these rules can be generalized, and that's just what we are going to do today. So this is 13.5 differentiation rules. So as I said, most of the rules that you know for taking derivatives we know from one-dimensional theory can be generalized to multivariate theory or even vector value theory. And that's what we're going to do today. In particular, most important rules are probably if you have two functions and you take their sum, then you can easily compute the derivative of that sum by just taking the derivatives of the summands. Then there is product rule, and there's chain rule. And those are probably the most important ones that we're going to summarize in a theorem. So here's how this works in higher dimensions. As usual, let X be a subset of R to the n and open. Let X star be an X. And let F at G be two functions from X to R, and let those be differentiable. At X star. Okay, then of course, the sum and the product of those functions are also differentiable. So F plus G and F times G are differentiable at X star with, well, first rule is simple. If you differentiate the sum F plus G at X star, then of course that's the same as just differentiating F at X star plus G at X star. Product rule is somewhat more involved, but it almost looks the same as in the one-dimensional case. So the differential of F times G at X star is the same as G evaluated at X star times the differential of F at X star plus F evaluated at X star times the differential of G at X star. And now for the chain rule, we'll introduce a new function. So what we want to do is we want to have the function f as the outer function, and we have a new function as the inner function. So that needs to map to x, to the domain x. So that needs to be a vector valued function. And let's say we have some new domain y, that be a subset of R to the m, be open. And we have a function h defined on y that maps to x. Okay, so that function be differentiable. At y star in y, where, let's say, h of y star equals x star. Okay, and what we want to look at the setting of the function f after h. That is then a function from y to r. Let me sketch that briefly. So we have y. Then we have the function h that maps y to x. Possibly not the whole of x, but at least part of it. And we assume that the point x star would be somewhere in the image of h. And then we have the function f that maps this result to r. Okay, and remember that point x star that was somewhere here in capital X. We had that point y star that would be mapped to x star, and then f would map that to some value f of x star. Or in other words, f of h of y star. Okay, and then the conclusion of that theorem is, so that function f after h is differentiable at that point y star at least. And well, the differential, what does hold for the differential? The differential of that function f after h at y star. That's chain rule. It basically works the same as in one dimension. So we first differentiate the outer function. So we take the differential of f. We evaluate that at the point h of y star. So at x star, at the original point. And then we need to multiply it with the differential of the inner function. So multiplied by dh taken at y star. Okay, so that's the differential of the outer function. And that is the differential of the inner function. Okay, in other words, if you wanted to write this in terms of Jacobians and gradients, so the differential of f is the transposed gradient. So what we could do here is that is the gradient of f evaluated as h at h of y star and then transposed times, and the differential of h is of course the Jacobian of h at y star. So one could do that. Or if you wanted the gradient right away, so if you want to compute the gradient of f after h at y star, then of course you'd have to transpose the differential. So that's d f after h at y star transposed. And that means you have to transpose this expression here. And remember, transposing a matrix product means also that you have to reverse the order of the matrices. So what happens if you do that is you'll start with JH at Y star transposed, and then multiply with the gradient of F evaluated at H of Y star. Okay, that probably looks more complicated than it actually is. So let's see 2 examples. And specifically, the examples will deal with directional derivatives, because those can be thought of as just this case here. So let f be a function defined on r to the n, mapping to r, be differentiable, and let's take a direction v in r to the n. It's not the zero vector. A direction and a point x star in r to the n. And then we can define a function h basically as the line through x star in direction v, or parametrization of that line. So we define h from r to the n as h of lambda is defined as x star plus lambda times v. Now that's a function from the reals to r to the n. And this function is a parametrization of the line. Of the line in direction v through x star. Okay, so what that means is f after h, that function, is basically the restriction of f to that line. Of course, h is obviously differentiable. And let's compute the differential. Well, we know that h of lambda is just x1 star plus lambda v1 down to xn star plus lambda vn. So those are the coordinates of h. And that means the differential of h at some point lambda, we'll just differentiate each of these functions here. And what we get is v1, v2, and so on down to vn. So the differential of h is precisely the vector v. Now what does that mean for the differential of f after h? At lambda? Well, that is the differential of f evaluated as h of lambda times the differential of h at lambda. That differential of f, well, that's just the gradient at h of lambda, and of course we need to transpose the gradient. And the differential of h, we've just seen that's v. So in other words, what we get here is, that's the partial derivatives df dxi at h of lambda times vi, and then sum this up over all coordinates from 1 to n. Well, what did we just compute here? Well, that's nothing else than the directional derivative, right? Because f after h is the restriction of f to the line defined by h. So that is the derivative of f along that line. That is exactly the derivative of f along the line defined by h. So that's the directional derivative of f at x star in direction v. So in other words, what we have just proven is, or seen, is that this directional derivative dvf at a point x star is precisely the same as the differential of f after h at lambda, where this point lambda is chosen such that h of lambda equals x star. Let's call it lambda star actually. And that's the same thing as the gradient of f at x star transposed times v. So to compute directional derivatives, it's actually sufficient to just compute the partial derivatives, the gradient, and then the directional derivative is just a linear combination of these. So directional derivatives are just a linear combination of partial derivatives. So this whole thing just became a whole lot easier, I would say. And let's do one more example to see that. Part B. Let's take a function f of x1, x2 defined by 1 minus x1 squared minus x2 squared plus 3 x1, x2. And you might remember that we talked about that function already. We computed a few directional derivatives. Let's say we're interested in the direction 1, 2. And we want that directional derivative. Well, what do we have to do? Now we can first compute the gradient of f at x1, x2. So differentiating that expression by x1, we get minus 2x1 plus 3x2. And differentiating with respect to x2, we get minus 2x2 plus 3x1. So that is the gradient here. And that means the directional derivative dv of f at some point x with this direction v here, that's the gradient transposed times 1, 2, or times v. So minus 2x1 plus 3x2 minus 2x2 plus 3x1 transposed 1, 2. So in this case, that comes out as minus 2x1 plus 3x2 minus 4x2 plus 6x1, or that's 4x1 minus x2. Okay, so once we have the gradient, taking directional derivatives for all directions is then just a matter of computing a scalar product. So with that chain rule directional derivatives just became very easy to compute. Okay, that concludes this discussion of differentiation rules for now. We see one more example in the next video, and of course there will be a bunch of examples in the exercises. So I'll see you soon.